So this is work that we've published on recently, where we talk about the obstacles that we see to automating alignment. So I'm going to run through that quickly. And this is work that was done with Marie, with Jacob Fau, and Jeffrey Irving. So just before we actually kick off, I think I'll start with some key takeaways. The first one is that we don't believe that solving scheming is enough to safely automate alignment research. The second is that we think we should be concerned about undetected systematic errors in automated research outputs, and these arise from automating hard-to-supervise fuzzy tasks. The third is that we believe this problem is relevant not just down the line, but it's relevant today to the early stages of automation, even when humans are writing the safety cases. We think these errors could be harder to detect in AI research, and it's possible that automation could slow alignment progress. And then finally, we think that the current scalable oversight protocols that we have are likely to be insufficient for what we need them to do. How's that? No worries. Cool. Okay, so these are the key takeaways from our paper. And just to give you a little bit of an outline of the talk today, I'm going to start off by presenting what a plan might look like to try and automate alignment research. I'm going to talk a little bit about this failure mode of undetected systematic errors. I'm going to explain why we think this is worse for automated research than the human baseline, and then talk a little bit about solutions and open problems. And there should be a lot of time for questions at the end, so please interrupt me if you've got any questions, but if you've got any larger ones, there should be loads of time. Okay, so a plan for automated alignment. Well, it might look something like this. You might want to build agents that can do empirical alignment work, confirm that they're not scheming, use these agents to build empirical safety cases or risk reports for each successive generation of agents, and eventually hand over primary responsibility for the research when the agents are outperforming humans. And so it might look something like this. Your humans might generate some research. They might vouch for the safety of your first generation agent. And together with humans, they produce more research. They vouch for the safety of the second generation agent. And so on. And in this way, you can bootstrap all the way to alignment of superintelligence. And over time, these iterations change. We expect more of the research to be taken up by agents as time goes on. So an obvious question is, why is this appealing? Why might we want to do this? And the reason that we might want to do this is because it seems that we've reduced a very difficult problem of directly aligning superintelligence into a much simpler problem of ensuring that we have a non-scheming research assistant to help us with alignment research. What's the goal of an automated alignment program then? What are we actually trying to do? We think the goal of an automated alignment program, or at least the output, is what we're calling an overall safety assessment. And you can think of this as an estimate of the probability that the next generation agent isn't scheming. And this is sort of like a generalization of a safety case. It could be evidenced by a safety case, by a risk report, by a lot of experiments. It could even be implicit through staff surveys. And we want it to be calibrated and also demonstrate that there's low risk. There are various ways that this plan could play out. We could be successful, we could manage to align our agents, and we could be unsuccessful. And within successful, we can either know that we've succeeded, or we can not know that we've succeeded. If we're unsuccessful, we could fail and know that we've failed to find an alignment solution. We could also fail, but not realize it, and fail because our agents are actually secretly sabotaging our alignment research. And then finally, we could fail, but not due to sabotage, just because there are undetected systematic errors in the research outputs that are generated by these agents. And this is the failure mode we're going to talk about today. Okay, so just to give you a little flavor of what we think this might look like, I want to paint a little sketch of how automation might look in the early and later stages of alignment. So the early stages, well, I don't know if you saw, but Anthropic published a paper recently called The Automated Weak to Strong Researcher, and this is the sort of flavor of thing we expect to happen during the early stages. In that paper, humans picked an alignment metric, in that case the performance gap recovered, and agents optimized against that metric. So in these stages, we think that agents are going to act mostly like research assistants, research engineers, research scientists. They're going to hill climb on metrics that humans are setting. They'll run experiments, they'll generate evaluation artifacts. But the humans are still responsible for proposing new directions, for setting and aligning the metrics for the agents to optimize against, and for aggregating all the information that they learn and producing overall safety assessments. And the key distinction here is that the humans are performing most of the fuzzy tasks. The agents are performing crisp tasks, but these contain many judgment calls in the details. So for example, an agent might make a particular decision about how it presents the results to the human researcher, and that could influence the conclusions that are made. And as automation progresses, we have this transition where agents perform an increasing fraction of harder to supervise and more load-bearing fuzzy tasks. So they may generate the actual new research paradigms, generate metrics, they might produce the overall safety assessments, they might even produce new scalable oversight processes. And the humans, a nice analogy that we like to use is that humans are much more like a funding body. So they allocate resources between different research agendas, they evaluate agent outputs, and possibly they evaluate outputs through agent-generated scalable oversight protocols. And there's a key concept that sort of runs through all of this, and that is hard to supervise fuzzy tasks. So what's a fuzzy task? Fuzzy tasks are tasks that lack clear evaluation criteria. So it's very hard for us to specify whether an output is good or not, and experts might disagree. So there are some examples. One might be identifying objects in images, another might be judging the quality of writing, and the third might be drawing conclusions from a research project. And a key property of these fuzzy tasks is how difficult they are for humans to supervise. And there's a spectrum from easy to supervise to hard to supervise. On the easier side might be questions like, does this image contain a bus? On the hard side might be something like, is this experiment evidence the model is honest? On the easy side, it's relatively easy for a human to identify what the correct answer is, even if they can't write down why. On the hard side, it's much harder for a human to identify whether the output is actually correct. Okay, so we just outlined briefly what a plan might look like for automated alignment, what it might look like going into the future, and we talked a little bit about these hard to supervise fuzzy tasks. And now I want to talk a little bit about the failure modes that result from it. Why do we care about hard to supervise fuzzy tasks? Well, research is going to contain undetected systematic errors because alignment contains a lot of these hard to supervise fuzzy tasks. And this happens whether agents are generating this research or humans are generating this research. And there's actually a lot of existing evidence for this. This is already happening. So this is from a post by Ryan Greenblatt where he says that agents are appearing more misaligned when performing tasks that are harder to verify. And this mostly contains tasks that are like difficult for humans to spot when the agent might have made a mistake. And the flavor of mistakes here is misrepresenting results, not trying hard enough, even if the task is within the capabilities of the agent. So hard to supervise fuzzy tasks lead to undetected systematic errors. There are two types of hard to supervise fuzzy tasks that we think are important for alignment. And they're as follows. The first is measuring what we care about. So in alignment, we can't directly measure the properties of the model that we actually care about. And that's because we can't safely deploy the model in a scenario where it could cause harm and observe whether it takes misaligned actions. So instead, we investigate alignment proxies. This is things like honesty evaluations, white box probes, model organism experiments. And the difficulty here is making an inference from your alignment proxy to the actual properties that you care about. And this inference, this judgment, is a hard to supervise fuzzy task that's pervasive in alignment. And the second type of hard to supervise fuzzy task that we think is important is this problem of aggregating correlated information. So when you're trying to form a safety assessment, you might want to reference thousands of alignment experiments. And aggregating those thousands of experiments correctly is very difficult. It's a difficult thing for humans to do. To give you a concrete example here, imagine you have 10 research outputs, and all of them tell you that agent n+1 isn't scheming. If you treat these as independent evidence, you might come to the conclusion that the probability of scheming is relatively low. But there's uncertainty in the conclusion of each of those research outputs, and this uncertainty is correlated. And if you mismodel that correlation structure, you can make mistakes when aggregating those research outputs and come to incorrect conclusions. And critically, this can happen even if every single one of your research outputs is correct up to the stated uncertainty. You might ask, where does this correlation come from? Well, there are three sources. First is the agents themselves. They have shared weights, there's shared training data, shared optimization pressure. The second is humans. So there are shared systematic biases between human reviewers. And the final one is the research process itself. So assumptions, shared methodologies, or conceptual frameworks. To give you a concrete example here, imagine that all of your research papers assume that the persona selection model is the correct model for understanding agent behavior. And there's correlation through that assumption. And the key difference between human-generated research and automated research is the agents. So this is the extra source of correlation. Okay, so we know what automated alignment might look like. We know it contains these hard-to-supervise fuzzy tasks. we know that these fuzzy tasks are going to result in undetected systematic errors, regardless of who does them. So the big question is, why is this worse than human-generated research? And it's worse because we believe that errors are going to be much harder to spot in automated research, for three reasons. The first reason is optimization pressure. So agent outputs are going to be optimized to look correct to human judges, but because alignment contains these hard-to-supervise fuzzy tasks, human feedback doesn't necessarily indicate correctness. And so the errors are going to be concentrated in the areas where humans are unlikely to spot them. The second is alien mistakes. So there's a different cognitive architecture between humans and agents, and so the type of mistakes that agents might make could be very different from the type of mistakes that a human researcher might make. And if you've got a human reviewer looking for these mistakes, or perhaps they're not looking in the right places. And then finally, as you move through this process of bootstrapping to sort of more and more capable models, you may eventually need superhuman arguments to justify your alignment solutions, and if your humans can't follow those arguments, well then they can't identify where the errors are. So a particular example about alien mistakes, let's imagine your agent is designing an evaluation, and it generates a long prompt for the model being tested. But hidden in this prompt is an accidental leak that the model is being evaluated. This is maybe a mistake that a human researcher is very unlikely to make, and so reviewers might struggle to find them. Now this is a very simple example, and you can imagine ways of finding this mistake, but it gives you an idea of the type or the flavor of errors that might be pervasive in automated research. Okay, and the second reason that we think it's worse for automated research than it is for human research is that automated alignment is different to existing human sciences. So as models are becoming more capable, we are less and less able to rely on iteration. It becomes unsafe to deploy the model and observe whether it takes misaligned actions. And there's a question here about to what extent can you rely on iteration or experiments of weaker models that are perhaps easier to spot whether they've taken misaligned actions, but the question is about how far that generalizes, and that itself is a hard-to-supervise fuzzy inference task. There's also a much greater volume of research. This poses problems for aggregating it and forming overall conclusions, and there's increased time pressure. So I'm just going to run through a couple of examples here about a few of the things that we're worried about. So one of them is, let's imagine that you're trying to choose between two different alignment techniques. In your first alignment technique, there's some alignment metric, and maybe that's an agent-generated metric, and there's some number associated with that. There are a bunch of papers that have been written. There's a whole load of compute that's been spent on that. And then similarly, for your second technique, there's a different metric, there are a different number of papers, and there's a different amount of compute. The question is, which of these techniques should you adopt? Well, this is a very hard judgment problem. It's not obvious to what extent metric 1 and metric 2 capture the things that you actually care about. It's also not obvious the extent to which metric 1 and metric 2 are the effort that has been put into optimizing those metrics. Okay, it looks like technique 1, there are more papers and more compute, but does that actually tell you that metric has been optimized harder than the other one? And the second example is, if you think back to the example that we gave about the early stages of automation, and we spoke about Anthropic's weak to strong automated researcher. In that paper, the humans were setting a metric, agents were optimizing against the metric. But eventually, the agents are actually going to set their own metrics. Setting metrics is a hard-to-supervise task. They're going to contain errors in the metrics that they come up with. And if you optimize against these metrics and produce more research outputs based on those metrics, you propagate those errors through the research base. We have these undetected systematic errors. They're going to be worse in automated research. What are we going to do about it? So the obvious question is, how do we train agents to perform these hard-to-supervise fuzzy tasks well? We increasingly can't rely on iteration. We are going to have to rely on the agents performing these tasks well themselves. And we see two paths to doing this. The first is generalization. So this is the idea that you might not be able to train directly on a hard-to-supervise task, but perhaps you can find a different training proxy. You can train on that. That's much easier, and perhaps that performance generalizes. And the second is scalable oversight. And that says, well, there's a hard-to-supervise fuzzy task over here, but perhaps I can decompose that into easier-to-supervise tasks and then recombine them in some way to get some training signal for the hard task. Let's talk quickly about generalization. So to give you an example, imagine that what you care about is designing experiments that reveal whether the model that you're interested in is honest. And that's hard to train for, so you think, okay, well, instead let's train on predicting the outcomes of existing honesty evaluations. And you can see why this might generalize. It seems like they're getting at the same thing, And perhaps in learning to predict the outcomes of the evaluations, your model is going to learn something about what it is that drives model behavior. So perhaps it learns something about honesty. But the obvious question is, well, how do you know? How do we validate these training proxies if you can't evaluate performance on the final task? We see two ways that you might try and do this. The first is predicting generalization. So if you're able to, given a training proxy, predict whether or not it generalizes to some actual target task, then you remove the need to evaluate that target task. The second is maybe you want to try and improve your ability to actually evaluate performance on the target task itself, and that's where scalable oversight comes in. So scalable oversight, well, we see two problems with current scalable oversight techniques. And the first one is this question about how reducible are these hard-to-supervise fuzzy tasks. If you decompose a hard-to-supervise fuzzy research task, it seems likely that the subtasks are themselves going to be fuzzy. An example here is, let's imagine that when you're forming an overall safety assessment that relies on some model organism experiments, one of your fuzzy subtasks might be how relevant is this particular model organism for determining whether or not the model that you're actually about to deploy is scheming. So there's this question about how much can you decompose these fuzzy judgment calls? Can you decompose them entirely into crisp tasks, or do they remain in some sense irreducibly fuzzy? And how fuzzy are those subtasks? Now, this doesn't mean that your scalable oversight protocol doesn't work and isn't useful. If your subtasks are easier to evaluate than your main tasks, you've still gained something here. The second problem comes back to this problem of aggregating correlated evidence. So we're going to use the example of forming a safety assessment here. Existing scalable oversight protocols assume that when you're recombining your subtasks, that recombination process is straightforward. So debate, for example, assumes that you can take a claim and decompose it into a deductive argument. But in actual fact, you might expect your subtasks to be probabilistic and correlated. And you might not know what that correlation structure is. So this aggregation, recombination process is actually very difficult. An example, you've got two papers. They both assume the persona selection model is correct, but they both use very different experimental setups. It seems obvious these are correlated in some way. Well, how correlated are they? What number do you put on that? This is a judgment call. This is a hard-to-supervise fuzzy task. And this is just between one single pair of research outputs. You might have significantly more complicated correlation structures between higher order correlations between many, many more research outputs. Okay. So I've given you a lot of problems. Just want to run through a couple of ideas that we have about how to follow up on this and how we might actually work towards solutions. We see that there are sort of three buckets of research that you can do. The first is measuring agents' ability to complete these hard-to-supervise fuzzy tasks. Maybe you don't want to just measure agents. Maybe you can even try and train them to do these. And this involves gathering data on hard-to-supervise fuzzy tasks. So one example is perhaps you've got research logs for some research project that you've done. And these might be intermediate documents, meeting notes, code from finished alignment project. You might want to try and measure the agent's ability to continue that project against the human baseline. And you might want to try and pull out, well, what were the fuzzy judgment calls that the agent had to make? Is another agent able to distinguish between, let's say, for example, you were doing a project, and at one point an agent proposed some next step to that project that was then later corrected by a human. Is another agent able to distinguish between those two things, between the human-generated solution or the agent-generated solution? So in this way, maybe we're able to benchmark or get some handle on to what extent this actually is a problem, how bad are agents at these tasks. The second bucket is scalable oversight. And one particular idea we have here is, let's imagine you're trying to form these safety assessments. And you've got a bag of 1,000 experiments. It seems very difficult to aggregate those 1,000 experiments into a conclusion. So you might say, well, let's make it easier. Let me ask the agent to pick out 5 of those experiments. And maybe that's a much easier process for me to aggregate. But now you're trading what is a difficult aggregation problem for trust in the agent's judgment about which of those experiments you should be paying attention to. And so maybe something that's better to do is to train agents to generate a small number of new research outputs that in some way encapsulate the findings of your original research corpus. And you can test whether or not that's a good compactification by getting another agent, like a weaker agent, to see if they can predict the outcomes of your original research corpus from this smaller compactification. this gives you a nice signal, a nice metric that you can test whether or not this summarization of information is actually capturing the relevant and important information that you learned. Why is this useful? Well, now you've got a small number of experiments that perhaps a human can go and verify and look at and check. And it might be much easier for them to actually aggregate to form these assessments, because there's only 5 of them, there's only 6 of them, instead of 1,000. And finally, generalization. So there's a question throughout all of this about how far you can generalize from training on easier tasks. And the question is, well, we don't know how far, but perhaps we can run things like simulated generalization experiments. So perhaps you can test training proxies by taking research from beyond the knowledge cutoff of a model and testing whether or not that have somewhat like some ground truth, and testing whether training agents on training proxies generalizes to them being able to actually solve these harder to supervise fussy tasks. There are many more things. I'm happy to talk about them, but I'm going to leave it there, and I've got a lot of time now for questions. So thanks for listening. And, yeah.
I just want to mention a couple ideas that came up during your talk just briefly. I'm sure there's lots more that people can think of, but I was just wondering about like breaking the correlation of failure types between agents by maybe using like a zoo of agents who've been trained with different like subsets of data or different architectural bases, like non-autoregressive diffusion language models that don't generate text in order but edit random spots in the text, maybe would give different biases. I was also wondering about this idea of maybe we can have agents not need to generalize as much in order to be useful agents if they're trained on very specific like scientific protocols, like this is how you evaluate a generic data set and present it such that we can be confident over a bunch of data sets that it follows this protocol, and then from there trust that it will do that on new data sets because it's less of a generalization if it's just following a protocol.
Yeah, great question. So the first question was about to what extent can we engineer differences between agents such that their outputs are less correlated, such that this becomes less of a problem. I think this is just objectively a good thing to do. I think that sort of regardless of whether or not you can engineer this, you still have this correlation problem, right? And it will remain in some sense, even if you can like get them completely independent in some way, because you still have correlations through the research process and through your human overseers. And so there's maybe an open question about to what extent can we extract like diversity in agent outputs. But I still think this leaves your problem of iteration on the table, right? So science usually works by this iteration process. Like I try something, I make a paper, someone else tries something from that paper, they realize I was wrong, we correct what I did, we move forwards. And you might hope that a sufficiently diverse set of agents can do something like this. And I think that's a fair hope. The worry, though, is that as you become less and less able to do this sort of iteration process, because at some point you have to make a decision about are we going to deploy this new model or not, is it safe or not, and you can't throw it out in the world, check whether or not it makes mistakes, whether it's misaligned, and then change your research accordingly. This becomes harder and harder and harder to do. So you're relying more and more on judgment calls from the human, from other agents about, is this research actually correct? There's also maybe another question about this iteration process that happens in normal science. It doesn't mean that we sort of constantly get more correct over time. There's this, the overall credibility of a field is going to fluctuate over time. And at any one point in time, you don't know where you are on that. Like, okay, is like my research like mostly correct, or is it mostly incorrect? You know that you've iterated and you've caught some mistakes, but you don't know that you've fully resolved it. The second question from memory was something like, can you train agents to do very specific subtasks and like follow particular scientific protocols? Maybe that means they're less likely to make mistakes. I think yes, this is a very good thing to do. You still have the problem of okay, if the subtask that you care about training the agent to do very well is one of these like fuzzy judgment calls, what's the protocol that we're writing down that we want the agent to follow? Well, we can't agree on that ourselves. To a large extent, we rely on sort of heuristics that scientists have and have developed over time, and those heuristics are often wrong. Like if you look back at the history of science, there are many examples where we've done things that have been totally incorrect. So if you look at, for example, physics, I was a physicist before this, for a long time, the luminiferous ether was a thing that was believed to exist, and this is the medium through which light was believed to propagate. But eventually, Michelson and Morley ran some experiments, and they demonstrated that that wasn't true. But for a huge amount of time, that was scientific consensus. So I think it helps, but I don't know if it solves all of these problems. But great questions, thank you.
Thank you for the talk. I have two questions that are essentially two different sides of the same coin. The first one is that it seems arguable that there's an inherent tension that, for the efforts to make things more monitorable or supervisable, there may be a tendency for the scientific communities to kind of converge towards developing agents or problems that may share more similarities, which arguably in turns might constrict diversity in one way, which in the totality may result in less diverse opinions in science. Do you think that could be a possibility? And the other question is, as scientific agents become more normalized, would it be possible, do you think the emergent risk of agents could be developed to have risk of scheming or hacking these metrics in the future, or collusion, that could be also a factor that we need to foresee and account for in possibly the near future?
Nice. I'll take your second question first because it's sort of front of mind, and then we'll go back to the first one. So the way I see it, there are sort of two things that we can worry about for automated learning. One is this sort of question of undetected systematic errors. Your agents are trying to help you, but they're kind of a bit rubbish, and they produce stuff that has errors, and maybe you miss those errors. And the second is your agents are actively scheming against you. I think that remains an important thing that we should worry about and we should investigate. I'm unsure to the extent to which we should prioritize one over the other. My leaning towards the sort of undetected failure modes errors that we've been talking about is that this seems like we're trying to automate alignment on easy mode. Let's assume your agents aren't scheming against you, and that seems very hard already. So if we're not going to solve this, are we going to solve the other one? Perhaps we need a little bit more time, or we need to put more research resources into actually solving this problem. But yeah, I think it's true that we should also remain concerned about scheming, that we should put resources towards trying to resolve that. Yeah, I think maybe something else is that over time it's going to become harder and harder for us to verify whether or not models are scheming, right? And that's a similar flavor of things, right? Like as your models become more capable, perhaps as they pass the human baseline, it's going to be harder and harder for us to find instances of misalignment, just in the same way that it's going to be harder and harder for us to find errors in the outputs they produce. So in some sense, they're similar parts of this problem. But yes, I agree. I think we shouldn't devote all our resources to trying to solve this problem. We should spread them across lots of different problems. Could you remind me of your first question? Because it's
the first one was more about attention, as if people are trying to make the agents more supervisable in general, that would create sort of like a creativity bottleneck of how science would be, because human science so far has been relying on different. You can touch on different methods, different diverse opinions to kind of move forward.
Right. Yeah.
Could this be creating a tension, a bottleneck on that?
Yeah, I think this comes down to perhaps that's true. But if you're in the early stages of automation where your humans are setting agendas and stuff, then I think this is just a question about how much research diversity do we have among the research scientists who are pushing the agents to do these various things. I think that's a big open question. For example, to what extent should we rely on theory? To what extent should we be putting more resources into conceptual research? To what extent should we be putting resources into the more empirical side of research? And how diverse is the research base? That's a good question. I think there are reasons to believe that, I'm not sure whether from oversight, for example, so maybe I've misunderstood your question. If what we're trying to do is match oversight to a human overseer, then I think if we succeed in that, then the diversity that we have is just the diversity between the human research scientists. But I do think that there's perhaps a problem, which which we spoke about. Let me just bring it up back. Ooh, here, for example, this optimization problem is a real problem. This is where we are putting pressure on these agents to produce things that look good to us and that are therefore perhaps correlated in the errors that they share, and those particular errors are also ones that are really hard for us to spot. So I think that's true, and that's definitely something we should worry about.
So first, just to check my understanding, like we spend a lot of time on fuzziness, and we care about fuzziness insofar as it makes tasks harder to supervise. Is that right?
Yeah.
My question is, like, what other factors make something harder to supervise? Like, I can imagine crisp tasks that are still relatively hard, or fuzzy tasks that are relatively easy. Like, what else influences that?
Yeah, I think the short question is, the short answer is, I don't know. Like, it's actually an open question to, like, we also don't even know. So if I go back to, there was a point where we spoke about, let me see, Ryan Greenblatt had this post where he spoke about, like, agents appear to be misaligned when they're doing hard tasks. And maybe one obvious follow-up question from this is, what hard tasks? And which particular tasks are the agents producing these failures on? And I just think we don't actually know. We don't have good information on this at the moment. But I think it's true that it's not just this, like, fuzziness. There are perhaps, like, crisp tasks that are difficult. Maybe crisp tasks are different in though that maybe just, like, searching for solutions and trying and failing things is a much more appropriate, like, way of trying to make progress on those, because you can actually measure whether or not you've made progress where you can't with these fuzzy tasks. So I think much more concerned with these fuzzy tasks. But I do agree that there are different dimensions of hardness, and we are very uncertain about A, which particular tasks we actually are going to care about, which ones are we really going to want the agents to do well, and B, how hard are they, how good are agents at these different types of tasks. I think it's a good open question.
What about, like, fuzzy tasks where there is consensus, though? Something like, is this writing good or bad? And the presence of, like, made-up words obviously makes it bad, and we all sort of agree on that, and you can present, like, a legible argument. There were made-up words, and that's why the writing is bad.
Yeah.
Like, does that let you do more of this kind of?
I think that's useful. That I sort of view that as, like, a medium hard to supervise fuzzy task. I actually think writing is a good one. Like, it confuses me slightly that there seems to be a strong consensus among people that agents are not very good at writing. And it seems that there are a lot of people who are good at distinguishing good writing from bad writing, and that maybe this is something we can actually make some progress on. There's, for example, many more people who can distinguish good writing from bad writing than people who can distinguish good alignment research from bad alignment research. So that's something there. But yeah, I think that's true. There are exactly tasks like that. Another thing that I would say about human consensus is that we can have human consensus on really hard tasks, but we can be all wrong, and that happens quite a lot. And that's what I'm really worried about. Like, things that really matter, that are very hard, that we have, like, very good historical evidence that humans are, like, poor at doing. Perhaps that's my answer.
Sure. Thanks. Yeah, thanks for the talk. Yeah, I guess I'm struck by the, like, question about whether this is actually sort of super unique to AI systems or something, and, like, basically the general problem seems to be you have, like, teams of researchers that are driven by incentives that are not, like, to find the truth. And it seems like there are maybe some lessons you could draw from, like, other settings where that's true. Like, I guess an extreme example maybe, like, if you're in a war or something and you capture some researchers and try and, like, get them to do productive work without sabotaging you or something. But then also, I guess, generally in, like, science, research is driven by things like, prestige or money or whatever that are not necessarily truth. And there it seems like some things like pre-registration or replication have helped to, like, cut down the rate of errors we have there.
Yeah.
So yeah, wondering if there's, like, other fields you can take inspiration from for solutions.
No, I think definitely we should. And things like, it might be that, like, having agents helps us with replication because we can run loads of things in parallel, and that's great. And I think we can definitely learn things from other fields. I think that the thing that perhaps makes alignment different in some sense is this, like, this failure or this inability for us to rely on iteration to the same extent. So we need to be, like, increasingly sure that the first time round we've got the right solution, which that does exist in other fields, obviously, but I think something that actually makes this problem in alignment much harder. But I do think that you're right, that there are things that we can learn from other areas that are trying to deal with similar problems. But even similar problems like this aggregation problem, where is the aggregation problem that we find it? Forecasting has to aggregate a whole bunch of correlated things. Safety cases for other industries, they have to aggregate a whole bunch of correlated information. Maybe they have good techniques that we can look at and use and try and adopt. So that's good.
This is a great question, Ola, because I was actually going to suggest something on the aggregation problem. One question is like, have you looked at bootstrapping rather than asking a model to select 5 different research experiments out of 1,000, just like randomly select 5 different out of 1,000 and then run this like 50 to 1,000 times and see kind of what the aggregate response is. So that's one thought on like whether you could borrow that from other fields. And another one is in psychology. So this question of like, how do we deal with agents that have correlated failure modes? In like psychology and social science, you can often look for mediating factors. So you know, you've got something that you're interested in measuring, you've got a couple of different independent variables, and you're like, you know, variable 1 affected the outcome 50% or like contributed like 50% towards the outcome that we're interested in, but like this other mediating factor kind of, you know, would impact things regardless of which, like, whatever variable 1 was set at. Have you looked at kind of like, could we understand which model design techniques result in more correlated model outcomes, or like whatever your metric 1 or metric 2 were, and then like maybe intentionally diversify the models or something?
Yeah. Yeah. On your first point about can you make safety assessments from like random subsets and aggregate them, I think that's a good thing to do. Seems good to me. I mean, maybe I still think there's a lot of judgment there about like at some point this becomes computationally infeasible for us to do, right? Like, and there's a judgment about like, well, which subsets are we going to look at, and how do we pick that they are like representative or useful? I think that somehow they're going to form an overall safety assessment that I actually care about. But I do think there's an avenue of things down there that are definitely worth exploring. I mean, I don't know if I fully followed your second question. I think it was something about. Can we look for things that are actually forcing correlations in agent outputs somehow? We can like they're this variable and like and I think that's definitely something we should do. And there's this question about, which I think you were pointing to as well, to what extent can we extract diversity from our agents? And maybe that's through some training processes, but maybe it's also through where we can look very carefully about like what are the assumptions that are underlying what they're doing, and to what extent they're correlated between the various outputs that they're producing, and we can try and force diversity in that way. And I think that's good. I think my worry about this lack of ability to rely on iteration over time, like the lack of safe feedback loops that we have, still bites. But I think these are all really good things. Maybe these are all really good things, and I think really what these are all getting at is, to what extent do we need high assurance guarantees for alignment now? And when do we need high assurance guarantees for alignment? And maybe one thing that I've been thinking about recently is this difference between fully scalable oversight and semi-scalable oversight. Semi-scalable oversight are things that sort of take you a little bit of the way. Like maybe they get us better performance on these hard to supervise fuzzy tasks. These are things you're talking about, some of the things we were talking about with these compactification ideas, that maybe they get us like a couple of generations down the line, and the hope, I suppose, is that a couple of generations down the line, well, your agents are better, they're clever in some sense, they're better at maybe some of the more formal or the theoretical aspects of alignment, and so perhaps you can try and at some point get your alignment solution that holds all the way. But there's this question about, well, that seems like quite a big bet to me. I think we should also be putting some eggs in the basket of like, let's try and get higher guarantees now, such that we don't have to rely on these other things that you guys were mentioning. It's a bit of an open question.
Yeah, thanks for the talk. I guess it seemed like in this work you're kind of taking a kind of realist perspective. So the reason why like proxies are bad is because we have this like actual thing that we care about, but the proxies are like not capturing it. I guess specifically for alignment, maybe you're thinking like there is like a notion of alignment that's kind of clear and crisp, and we're kind of like aiming for it. But I guess my prior would be something more like, there's a bunch of things that we still need to decide that we like. Maybe we don't know like what the questions are, but maybe this is some kind of like societal level things that we actually need to decide on. And maybe this kind of needs to be part of this alignment research. It's like kind of surfacing these questions so that we can actually make these decisions. And I feel like if we just kind of let the agents make these decisions, they may take decisions that we wouldn't be happy with, or maybe some people wouldn't be happy with, or something like that.
Definitely, yeah. I think I have two responses to that. One is that there are some things that are relatively crisp, not relatively crisp, but that we have like some consensus of that are things that we need to work on. We've made, I think, a lot of progress in understanding what it means with like scheming, deceptive alignment. But you're right. There is one thing I think the field would definitely benefit from is work trying to actually define what are these open problems that we, like, let's say tomorrow I give you infinite compute and 1 million agents and I say, right, solve the alignment problem for me. Where are you putting them? What are the questions that you really want answers to? I think we sort of pointed to some of them. I think some of them are things like, can you get a really good scientific or predictive understanding of generalization? That seems like that would really help a lot. So I think maybe there are two answers to that. But I agree with you. There is work to do, valuable work to do in just like clarifying definitions of things and precisely what the aim of various research agendas are and what we are trying to solve. And I agree that it seems like maybe a bad thing to do to rely entirely on agents to do this. I don't think that anybody is necessarily planning to do that, but it's something we should have in our mind, definitely.
Great, awesome. We'll take some questions from Zoom here. Do you think debate can be used as scalable oversight technique that could even hold for fuzzy, hard to supervise tests?
Yeah, so let me get this up. Yeah, so debate's great. I still think, and this is, I think, what these two sort of slides are trying to get at. The idea that, like, it's unclear the extent to which we can, debate relies on taking a claim, breaking it down into easier claims, checking the easier claims. It's unclear the extent to which, for these fuzzy tasks, we can break claims, difficult claims down into base, like, subclaims that are, it's still easy to verify. There seems to still be this, like, fuzziness difficulty. I think that's still an open question. And the second one is that, like, debate is assuming that you've got subtasks that are, like, you can recombine and decompose them easily, but you don't have this probabilistic correlated subtasks, and you also don't have this like question of, well, like even if I had a nice way of dealing with these probabilistic correlated subtasks, what is that correlation structure? That's a sort of judgment that a human scientist or even an agent has to make in order to find that correlation structure to recombine them. So I think that debate seems great, particularly for certain tasks that are like you can imagine, for example, you have a proof for something and you want to check that proof and you've got a very, very well specified thing and you can do this decomposition and check all the bits, and that seems great. And I do think that debate gets us a lot of stuff. But I think that these are maybe with the remaining questions that I would have about whether or not it's sufficient for these fuzzy tasks.
Great, thank you. Another one came in. Suppose somebody says that automating alignment research is just a crazy idea and should be far from our default plan. What's your reaction? Do you strongly disagree?
I think the obvious response to that is, what's your great alternative? And I don't see one. And it seems to me that it is the default plan. It is, you know, there are problems with the plan, obviously. There are reasons to be optimistic about it, you know. So maybe you can try and do two things here. You can or three things. You can try and come up with a better plan. I think that's great. People should do that. Particularly, I think there's theoretical work to be done there. Two, you can try and make this plan better. That's what this is trying to do. Three, you can say, we don't have a plan, these plans are all terrible, we should think about this more. I think those are the three things to do, and then which one I would pick precisely.
To what extent do you think that it's feasible that scaling the human element, like you could do some scalable oversight and you could do some alignment research, but you also scale the human effort that's going into the task.
Yeah.
You know, it's much harder to assess whether this fuzzy subtask or this, you know, this research task is being answered correctly. So we're just going to put like 10x man hours and we're going to block the project until it's done. Like if there was some sort of mandated regulation or enforcement of this type of human scaling as well, do you think that this would solve the problem, or do you just think this is just infeasible, or what are your thoughts?
Yeah, so I think this is just obviously a good thing to do. You can sort of think of scalable oversight as having two parts. One part is just like, without agent assistant, make humans better at giving oversight on this particular claim. And the second part is like, you know, with AI assistance, like what protocols can you write down? Debate, for example, is one of those. I think it's definitely a very good idea for us to do that sort of thing. In fact, this is the sort of thing that actually we're thinking about a lot in the alignment team at AC. We have cognitive scientists thinking about this. Like, how can you scaffold the humans such that they like debate between themselves or come to better supervision signals, and then maybe you can combine that with some generalization understanding and some better scalable oversight techniques, and maybe that kind of gets you some of the way. So I think that's definitely a thing that we should do. I mean, it seems like that is fundamentally limited in some sense. You can't go all the way with that, like just. But I mean, maybe I'm wrong. I think I would be less keen on like regulations to do precisely this and say, you know, dictate from on high. This is exactly the number of humans you should have on this particular problem. This is exactly how to do it. It just doesn't seem that's it's going to work, or that's going to be particularly efficient, or that's going to get us to the truth, the answers that we actually care about. But more human resources and more thoughtful, more thought about how we actually get this information from humans, it seems very good.
Yeah, thanks for the great talk. So there's the assumption in the talk that like all of these fuzzy tasks are assuming that the agent is not scheming against you. Mm-hmm. So if you assume that, like the question is, how different is supervising hard to specify tasks from just like general capabilities work?
Yeah, good.
Like it seems like we just get better at this by just more pre-training or like just getting more intelligent models and not like doing any alignment work in particular.
Definitely, I think this is a really, really good question, and it's actually something that I'm still confused about. Maybe, so to state the problem, it's that I think there's an implicit claim in the paper that there's a fundamental difference between alignment science and capability science, in that one is more metrics driven and one is more fuzzy. I think that currently is true, but they certainly seem to be moving closer together. There's increasing overlap. And I think the question is, how far does our capabilities training generalize to the specific things we care about? And in order to answer that, we need to know what are the specific things that we care about. What are the fuzzy tasks that are somehow specific to alignment, that are maybe not going to be directly trained on in capabilities work? And I can think of a couple of things here, but I'm sure there are more, like things like these safety assessments, risk reports, threat modeling. These seem like hard to supervise, conceptual, fuzzy, difficult tasks that maybe you wouldn't expect that by default the capabilities to work to make progress on. And there's a question about generalization. We don't know how far we're going to generalize from one hard to supervise, like one domain of hard to supervise tasks, to another domain of hard to supervise fuzzy tasks. So I think there's still lots of work to be done there, understanding that. But then I also think there's something about timing. Is it better to push really hard and make many types of hard to supervise fuzzy tasks go well? Or is that just making the problem worse? It seems like at some point you're going to need this to happen. My very uncertain belief at the moment is that if you leave this up to capabilities only, what you will get is better performance up to the human baseline in certain domains of hard to supervise fuzzy tasks, and that will not generalize as far as you hope that it will generalize, and that we should put effort into identify what are the things that are not going to be done by capabilities work that we want to be done that are important, and get solutions for those. And the second worry I have is that that will get us to like human level. That's still concerning. That doesn't seem like it's going to get us much past human level, and that's why you need these scalable techniques, scalable oversight techniques, where you can be like, okay, I have an answer, it's superhuman in some sense, I actually want to evaluate that, how do I do that? But I think it's a really, really good question, and it's something that we're we are a little uncertain.
Probably have time for one more question.
I'm being talkative today, but I think this is not more a question, but a little bit more of like a commentary because I work with a lot of scientists in cross-interdisciplinaries. And I feel like there's an inherent different threshold of distrust of AI agents in a lot, in certain fields. And I think these works, I really want, like frontier of amenable to fields that are more like AI, mathematics, physics, biology, the STEM field that have inherently clearer, I would say, decomposable subtasks. And it seems like, some of the other areas that are a bit less, for lack of a better word, fuzzy inherently, like, psychology or something like that, that may be a little bit harder to kind of like port this, or one, port this sort of framework over, and two, convince practitioners themselves to adopt this strategy, or this sort of like paradigm. And I think that that also like a field building kind of area that we might need to. It's really interesting to remains to be seen how the rate of adoption will cascade to other more, I would say, interesting, but no less interesting and important areas of science as well. So that's like my 2 cents on where I think like the field is probably heading in this direction, or the fields, yeah.
So agents are going to be used in other fields. I think that's true, and maybe we can learn something from that. I think your first point is something like some domains seem crisper and fuzzier than other domains, vice versa, I think this is actually one thing that we've been thinking about, and we're a little worried about. It's perhaps an open question. Is you can imagine some spectrum from, okay, I want to know whether my agent is aligned. I can run one experiment, and if I run that one experiment and I check it very carefully, I can definitively tell you whether this agent is aligned. All the way through to the other end of the spectrum, I have to run lots and lots and lots of experiments, and none of them are very good, and I have to make some sort of aggregate conclusion that sort of weighs everything up. And that's maybe more the psychology end of things and the sort of physicsy end of things. My instinct is that we are closer towards the second end of things. We've got a lot of evidence, none of it is that good. Maybe we're a bit confused about whether or not it has a load of errors. Maybe we don't trust it fully. We're going to have to combine it in some sense. We're going to have to come to a conclusion. It's going to be increasingly hard for us to do that. We may even have like increasing distrust in that evidence because of all of these things we're talking about, because of these optimization processes and stuff. But it's true, maybe, right? There are really good like experiments or theoretical guarantees or results we can prove where we're like, right, great, that has given me a lot of clarity, and that's really reduced the number of pieces of evidence and the information that I actually rely on in order to make this decision. So I think that's an open question, and we should not give up on trying to push ourselves more in this direction. But fantastic question.
Awesome. Well, thank you, Alexander, for coming out today.
Thanks for having me.